Really? Well, if you've got a lot of questions, go ahead and start asking them. Discussion board for today. I figured y'all would have a question about that. That's the wrong class. All right, so we have the reaction. 8H plus AQ plus manganese 8 oxide plus 3, 10 plus 2. Goes back and forth. I know it's sort of written there. 4H2O liquid plus 3 manganese plus 2 plus 310. So 4 questions it's going to ask. What's the standard reduction potential? How many electrons are transferred? What is Q and what is the voltage? Oh, Squeaky gets enough snuggling. She's been sitting on my lap most of this morning. She needs to settle in for her midday nap. Anyway, standard reduction potentials. Now, standard reduction potentials are actually pretty easy to calculate, but there are a couple simple pitfalls. So when we say standard reduction potential, if you go to the final exam packet on the course website, and I'll bring it up for you right here. There are these tables of standard reduction potentials. Now there's 2 types. There's standard potentials by standard voltage, and the reason it's arranged this way is that the most negative voltage is on top, the most positive voltage is on bottom, and then by reductant is an alphabetical listing of the elements. So carbon, chlorine, copper, hydrogen, iodine, nitrogen, nickel, phosphorus, etc. So these tables are the exact same numbers. It's just that we present them 2 different ways to make it easier to find the information we're looking for. So we work with the top table if we're looking for a particular voltage, and we work for the bottom with the bottom table if we're working for a potential reductant. Now, we don't have tables of standard oxidation potentials. The reason we don't have tables of standard oxidation potentials is because it's just the negative. So the opposite of oxidation is reduction. So if you have a reduction potential and the reaction is really oxidation, you flip the number. So the first question it's asking you is how do we find the standard reduction potential, which is E naught cell. And to do that, what we're going to do is we're going to subtract the reduction potentials between what's being reduced and what's being oxidized. And the reason we're going to do this is that the cell voltage itself is really the reduction reaction plus the oxidation reaction. But we're only given tables of reduction potential, so to convert that reduction potential to an oxidation potential, we just take the negative number. So in this reaction, you need to be able to identify what's being reduced and what's being oxidized. So easiest thing with any type of reaction, redox reaction, look for something that's an ion by itself. So we have 10 here going from +2 to 0. So this is the reduction reaction. If you looked at manganese, that's weird. I think these are flipped actually. It may have been one of the issues you were having, which is weird because I swore I copied and pasted this problem from something else. Oh my goodness, they're flipped. That shouldn't be 10 plus 2. That should be 10 on the left side and 10 plus 2 on the right. So I will fix that on the discussion board, but this is really supposed to be the oxidation reaction. And this is the reduction reaction. So how do we figure out the potential? Well, if this is the reduction reaction, we just had to look at the reduction potential for manganese going from MnO4 to Mn plus 2. And so if we go to our tables and we look up manganese, honestly, you may actually have to go to, wow, why is Chrome crashing on me right now? tables. If you will go to, and I'll flip it so you can see it, lessons, final exam material, I actually give you tables of standard reduction potentials. None of these are going to be on the final. The reason being, this is a much more lengthy list, so it makes it easier for me to give you different problems. That said, on the final exam, you're only going to need these tables of reduction potentials that are found in the packet. But anyway, it's going to work the same idea. We're going to scroll down. We have the manganese reaction here, MnO4 plus H plus, 5 electrons goes to Mn plus 2. That's 1.507 volts. And we need the reduction potential of 10 going from plus 2 to 0. So if we scroll down this enormous table, we've got that reaction here. So that's 0.151 volts. Yeah, for those of you who just lost audio, Chrome just crashed on me. So you're kind of hearing the interrupt while Chrome was crashing. So in case you missed any of it, to figure out the standard reduction potential, you have to figure out the oxidation and reduction reaction. I flipped these by accident in the problem, so I'll correct them on the discussion board. This should be 10, not 10 plus 2, and that should be 10 plus 2 on the far right side. If you go to the table of reduction potentials, and there's a big, long list of, it's a thick table, but it's every redox reaction. The reason I give you that is so I can give you more options in terms of redox reactions. The final exam is going to have a much shorter list on it. The reduction potential to take MnO4 to Mn plus 2 by the table is 1.507 volts. To take 10 from 10 to 10 plus 2 is 0.15 volts. So to find the reduction potential, it's just 1.507 minus 1.51. So if you work that out, that's 1.356 volts. So that's just the reduction potential. Now, a few comments on reduction potentials. You don't have to multiply. So here we've got 3 manganese, and I should have the 3 over here as well. It doesn't matter if the reactions multiply 3 or 4. Reference voltage is always on a per electron basis, so it doesn't matter how many electrons are being transferred. The same thing is true of the reduction potential reaction. So the fact that we've got a 3 in front of the Sn, we don't have to multiply the reference voltage of the Sn by 3. It's already normalized the number of electrons being transferred. So it's literally just one reference voltage minus the other. The only real complication you should be getting with this is if you have a negative reference voltage and you're subtracting it. So just keeping track of those positives and negatives. But that's the first question. What's the reference voltage? In this case, it's 1.356 volts. The next question is asking you, oh, come on, enemy discussion boards. How many electrons are being transferred? In this case, we have manganese going, actually the easiest one to do is 10. So we have 10 Sn going from, there should be 3. We have 10 going from a 0 to a plus 2. So that's 2 electrons, and we have 3 10 atoms doing it. So we have 6 electrons being transferred. So 10 is the easiest one to see. It goes from a 0 to a plus 2. There's 3 of them doing it. Is this reaction balanced? It should be. I'm going to check because you're making me kind of question myself now. But yeah, the reaction should already be balanced for the one that's online. In fact, let me check it right now. It should be balanced. That's weird. I know I copied this from somewhere. For all these reactions, just assume they're balanced. So whatever you've got written, just treat them. And if it's mistakes on my end, the mistakes on my end. I'm never going to make you balance a redox reaction and do all this Nernst equation with it because there's just too many places to go wrong. Because I don't think there should be a 3 in front of that Mn plus 2. But otherwise, it would be balanced. So yeah, just leave off that 3 in front of the Mn plus 2. And again, I'll change this on the course website. So next question to ask you is, what is Q? And there's a reason why it's walking you through this process. Q is the same Q it's always been. So you've got your concentration of your aqueous species. You've got your Sn plus 2 to the third power, your manganese plus 2, and your concentration of H plus to the 8th power. So you're actually given these numbers in the discussion board. So you're given concentration of tin chloride. Oh, I guess I could flip it so you can actually see it. You're given that your concentration of tin chloride, which will be your Sn plus 2, is 0.1 molar. You're given the concentration of the manganese plus 2 here is 0.2 molar. And the concentration of H plus here is 0.01 molar. So you would just plug these in your expression for Q, and this would give you your value for Q. Hold on. I know. Sorry, give me 1 minute for technical difficulties. I'll be right back. Oh, please feel free to go hug your cat if you need it. This is a live stream. You can always come back to it, right? So yeah, I got my workbench over to the right. She kind of got like wrapped up in the workbench. So had to get her out. Anyway, getting back to what we were talking about. You're going to get a number for Q. The reason this problem is walking you through this process is that ultimately you're trying to use the Nernst equation. And there's two things here that you have to have for the Nernst equation. One, you have to have the number of electrons transferred. And the second is that you need a value for Q. Now, the Nernst equation is actually something you've kind of already seen before. Was oxidation state. So this relates to last week's discussion board. Yes, if you can't figure out what's being oxidized and what's being reduced, and particularly if it's oxidized or reduced, you're not going to know where to stick it in the reference voltage formula. If it's being reduced, you're adding it. If it's being oxidized, you're subtracting that reduction potential. So this discussion board was meant to kind of get you on a footing where you can do this. Now, the way this ties back to earlier material in the class, and this is, honestly, it's something I wish we could talk about in person. I personally think it's cool. Earlier in the semester, we had this relationship, delta G equals delta G naught plus RT ln of Q. And when we talked about equilibrium for test theory, we said that there's the reference free energy change, the delta G naught, and there's what it actually is based on the conditions you're actually at. So you're not at 1 molar everything. What is it really? This is actually what the Nernst equation is based on. And all the Nernst equation is just converting units. So to get to the Nernst equation, we just multiply by minus 1 over NF. N is the number of electrons. And F is Faraday's constant, 96.485. All these do is take us from units of kilojoules per mole to volts per electron. So your Nernst equation, E of the cell, the actual voltage, is the reference minus RT over NF ln of Q. So again, the difference between delta G and voltage is delta G is kilojoules per mole. Cell voltage, or electrochemical potential, that's just volts per electron. reason we use this negative is that a reaction is spontaneous if it has a negative delta G, because we're losing energy. We want our voltages to be positive, so that negative kind of flips that connection. If a delta G is negative, that gives you positive voltage and vice versa. This NF is going to scale us to number of electrons. Now, there are some books that leave off basically this RT over F, and they reference it at 25 degrees C. It is a stupid approximation, and that is what it is. It is a stupid approximation done by older chemistry textbooks because they don't really know how electrochem works, and I have seen this in your books. Use this RT over NF because it's applicable at any temperature and any number of electrons, so it doesn't limit you to the 25 degrees C. What's the second E? This is your reference voltage. So that was the first thing it asked you to calculate, was your reference potential or your reference voltage. That's why you need it. It's basically going to get you your reference Gibbs energy, your delta G naught. So you need that, and it's a physical constant for that particular reaction. So now when it asks you, can you find the voltage, that 2 points, all you have to do is plug in the numbers you had from before. So you're going to plug in the number of electrons, which is 6. Whatever number you got for Q, R here is 0.008314 kilojoules per mole. It's your ideal gas constant. Faraday's constant is a 96.485. If you go look at the packets, it's on there as well as the value for R. T is temperature in Kelvin because you are working with thermodynamic values. This and this, so your E cell and your reference voltage should be close to one another. So typically we don't see like shifts away from like more than a half a volt. So it's N times F, number of electrons times Faraday's constant. So it's in the denominator. In fact, let me see if I can find formula sheet for the final exam. So I'll bring it up so you can see it. The formula sheet on the final exam is going to be a little bit cleaner than my handwriting. But it's this equation here. E cell equals E cell naught minus RT over NF times the ln of Q. And again, it's going to be analysis to the earlier Gibbs relationship that we worked with. So that delta G plus delta G naught plus RT ln Q. It's that equation times negative 1 over NF. Give me 1 minute. All right, what other questions you got for me? Should have been that problem statement. Alas, it was not. 25 degrees C. Man, where did I get that problem from? Again, I'll update the discussion boards and reflect this. Equation for Q. You probably will get an enormous number for this, particularly because you're dividing by 0.01. So your expression for Q here and again, that shouldn't be a 3 in front of that MN. I'll correct that. So Q is the concentration of tin plus 2 to the third power times the concentration of manganese plus 2 all over the concentration of H plus to the third power. In the problem statement, you're given the concentration of 10 plus 2 is 0.1. Concentration of manganese as 0.2. And the concentration of H plus is 0.01. So bring up Excel really quick. So we got 0.2 to 2 times 0.1 to the third power divided by 0.01 to the eighth power. And when I get that, I get like 2 to the 15th power. So if you're getting an enormous number, like in this case, 2 times to the 15th, that's actually fine. You're going to get huge values of Q because we do have these kind of H plus concentrations involved with it. Write out number 2 and number 3 at the KSP lab. Okay, actually hold back, go. Hold on, there's a few questions further back. So F, Faraday's constant is 96.485, not 91.485. So if you go to the packets online for the current material, it's going to have the 96.485 listed on top. Now the number of moles N is not moles, it's number of electrons. So you get the number of electrons by looking at the number of, in this case 10 was the easiest. 10 goes from 0 to a plus 2. There's 3 of them, that gives you 6 electrons. In terms of more time to answer the discussion boards, you never have a cutoff time. You're always allowed to answer them when you get to them. I would rather you do them than not do them. You have a cutoff for attendance reasons, meaning that I'm just going to count you absent if you haven't answered the discussion boards by Friday. But please go back and do them if you haven't had a chance. I'm going to go back and grade them as long as I see it needs grading. I'm going to grade it. The due dates are more to give you a feel for where you should be in the material by this point in the semester. So by today, you should be able to use the Nernst equation, assuming the problems are correct. They're in the packets and they are on the homework. But by today, you should be able to do the Nernst equation. Now, in terms of the expression for Q, be careful between solids and solids and liquids are going to be the big ones. So I do need to correct the problem. It should be 10, 0 here, and 10 plus 2, not flips, not the other way around. But that said, solid 10 does not appear in the reaction because it is a solid. So Q ignores solids and liquids. Only anything that is aqueous or gaseous needs to be involved in that expression for Q. Now number 2 and number 3 on the lab. So let me bring that up. So number 2, design experiments to determine the value of the constant for each solid completing the effect. Write out your procedure, show sample calculation. Basically, write that out as you would expect a lab procedure to be in the lab. So step 1 would be pick the salt, add so much. Basically, again, what you'd expect to see in the lab manual. Now, in terms of writing a conclusion, it gives you A, B, C, D, E. This is more just a qualitative reflection on what you saw. So based in terms of the calculations you ran, which one kind of gave you the number closest to what you expect for KSP. And again, you can just be kind of technical in this. The one that gave the best data were the ones that the data seemed to work out. The ones that gave you the poorest data were the ones that you tried to do the calculation and you weren't getting close to that particular KSP. In terms of published ones, you can just use the ones that are found on, actually most of these, if you just Google tables of KSP, you will find tables of KSP. And in terms of solubility rules, again, you should kind of know the solubility rules at this point, but you can talk about how KSP kind of compares to those solubility rules. Okay, so does temperature have to be converted to Kelvin for the Nernst equation? Yes. So if you're working with Nernst, it's backtracking to Gibbs, so it has to be in Kelvin. Oh, looks like you'll answer that question for us. Yes, Isaac, thank you for pointing that out. If you have the ideal gas constant, you are automatically in Kelvin. The 0.01 for the H plus concentration. So it's actually raised to the 8th power here for the 0.01. So it's not 2 or 3, it's to the 8th. The concentration of the 10 I think was 0.1, that's raised to the 3rd power. If you keep getting a small number, what's your definition of a small number? That's actually a pretty impressively large value for Q. That large value in Q actually implies that we're way above the equilibrium constant KQ, so it makes sense to say here that the voltage is probably going to be very small, meaning that the battery has probably pretty much reached equilibrium and is a dead battery now. $1.37? Well, your reference voltage is like 1 point something. So typically, most problems, you don't see the voltage shift more than 25% away from the reference voltage. In all actuality, and this is just practical, any battery you buy, and this is why voltage is so nice, is going to pretty much keep a constant voltage until like minutes before its death. So the reaction has to get really close to equilibrium conditions before it will actually go to a 0 voltage. And even then, it's a sudden steep drop off. But typically, voltages you don't see go much above 2 volts. That's usually something like a lithium ion battery. And that's something where they've really driven the concentrations to get you a high voltage. But voltages are typically 0 to 2 range. This isn't delta G where you'd expect to see like 25 to 150 and sometimes as high as 250 or 350. Voltage is usually kept very small. Yep, the unit for the E cell here is voltage. Now, when I used to teach this, I used to use voltage, and that was because that was just sloppy nomenclature I picked up when I was a postdoc and a grad student. E here refers to electrochemical potential. It is not the same thing as V. They both have units of voltage. Okay, so Camille got 2 times 10 to the 12. That's Q. I think Abby's referring to the E. So you have to put Q into your Nernst expression. So the Nernst expression, the cell is the reference cell minus RT over NF ln of Q. So you're going to put your value in for Q here. You've got 6 electrons transferred. Temperature we're going to say is 25 degrees C, and I'll update the discussion board to say that. F is 96.485. Yeah, 96.485. That Faraday's constant, if you download the packets online, they do actually have Faraday's constant listed at the top. R, 0.008314. So again, that 2 times 10 to the 12 should be referring to Q. It shouldn't be referring to the voltage itself. If you're getting huge voltages, odds are you're not using the right value for R. That should be 0.008314. N and F here are going to be several hundred. So R times T all over NF ends up being a very tiny number. Doesn't matter how big Q gets, Ln tends to crash it down into smaller and smaller numbers. Yeah, that's the unfortunate thing about a 15-second lag. So I would agree with your value for Q being that. Your voltage, you still have to plug into this equation to get your cell potential. You're going to want to keep it in kilojoules, not joules. The big reason this value for Faraday's constants, the 96.485, that's kilojoules per volt equivalent. So that volt electron equivalent gets rid of the units on the electron. If you work with 8.314 joules per mole Kelvin, you have to convert Faraday's constant to 96,485. You're better to keep it in 0.008314. Anyway, 96.485 is the most common reported value for Faraday's constant. It's what all the practicing electrochemists use because nobody works in joules. They're way too small. So yes, for the lab, I had to make it a little bit hard for you, right? For the lab, it's equilibrium. Go ahead and build your IC table. So let's say you worked with something like lead fluoride, PbF2. Going back to lead plus 2. And fluoride. You've got your expression for Q. In this case, it's concentration of lead times the concentration of fluoride squared. It is easier in this regard, so it gives you the number of atoms of lead and fluoride dissolved. Now, there are two approaches you can do for this particular lab. So one is to build your IC table. I would recommend you do it just to get the practice again with the IC tables. So you have 0, 0 plus x plus 2x. So we end up with x and 2x. KSP, if we plug it in, is going to be x times 2x squared. One option, well, you got to do this for either one anyway. Take the number of atoms of one element. So let's say it tells you that there are 45 atoms of lead plus 2 in solution when you've got equilibrium. You're going to take those 45 atoms and convert them to moles using Avogadro's number and then divide by the volume, which does give you super teeny tiny liters. That will give you the molarity of lead. You can stick that in here, solve for x, and then plug in for x. The other option, you can figure out the atoms of both lead and fluoride. So once you find their concentrations, you can stick them directly in for the lead and fluoride concentrations, and that will get that'll get you KSP as well. So you can either solve for extended reaction. You got to find the molarity of one of them anyway. The program is designed to work out, so yeah, both ways will work. X is your extent of reaction and tells you how much of the solid would dissolve. You don't necessarily need X to solve these types of problems because you have the concentration. That said, if you know the concentration, you can find X, and then if you know KSP in terms of X, you can just plug in X. Now I'm debating what the value of the voltage is, so let's see if I can figure it out. The reference voltage. Could someone post the reference voltage really quick? Otherwise, I got to go back and try to figure it out. It's 1 point something. Yes, so if you can, well, it's not moles. If you convert the molarity, the ions converted to moles divided by the volume will get you the molarity for the last row of the E table. So the reference voltage, thank you, Isaac, 1.356. So I get 1.23 volt, 1.235 volts as the reference volt, as the voltage of the cell. So 1.235 volts is what I'm getting using that 10 to the 12 number, 2 times 10 to the 12 number for Q. .356 sounds right. I think that's what I got earlier, because I think it's 1.5 volts for the manganese, and I think it's roughly 0.15 volts for the tin. T is the temperature. I accidentally left out of the problem. You're going to use 25 degrees C, which you need to convert to Kelvin to get to 298. But I'll correct the discussion board to make that a little bit clearer. Temperature will be given to you. This is kind of, I don't know where I got this problem from. Now I'm thinking back, I think I copied from something else, but it looks like I left off a few details. But yeah, temperatures should always be given in these problems. The whole point of the Nernst equation is so you can work at any different temperature. So Faraday's constant. So F in all its glory is 96.485 kilojoules volt electron equivalent. Kilojoules and volts here are meant to cancel out the kilojoules and the R and put the volts on top. This electron equivalent is meant to cancel out units of electrons. Yeah, your calculator is using 96485.33 because it's working in joules per mole Kelvin. Drives me up the wall as somebody who practiced electrochemistry for years. It's 96.485. But if you do that, you got to work with an R value of 8.314. So the lab, that part 2, Abby's asking if the lab only gives ions, not weight, how are we supposed to reference that? You're building a procedure based on the simulation. So not how you would do it in the real world, how you would do it in the simulation. So you'd say something like add enough of the salt until you see undissolved or bound ions, because you don't want to add so little that it's all dissolved. You want to add enough that there's still particulates in the simulation, and yeah, just basically to make that in your procedures how you would do it. Electrochemistry is kind of a weird field. Only recently has NC State been teaching electrochemistry at the undergraduate level. Traditionally, it's been reserved for the graduate level. There are 2 major reasons for this. One, our curriculum dates back to the 1960s when oil was big and electrochemistry was not. The second is that there is actually a shortage of electrochemists. It is a dying field. Most of the people that are practicing electrochemists are like in their 60s, and I say that without exaggeration. They're in their 50s or 60s. So a lot, and I saw this when I started teaching Chem 2, a lot of the textbook was written by people who are clearly not people who practice in the field. And if you take me for organic, you'll see this. I clearly didn't practice organic chemistry in the field, so you'll see me making references saying like, yeah, it's not quite right. I see this a lot with the textbook. You see the 96,485 because you deal with people, it was written by people who didn't practice in the field. So to them, the units, a joule and a kilojoule are just interchangeable, so they worked with joules. The practicing electrochemist is going to tell you to use the 96.485, and the reason they're going to tell you that is that all their calculations are in kilojoules because electrochemists are so thermo-heavy, and thermodynamics relies in kilojoules. But if you don't know that, you think joules and kilojoules, what's the big deal? Well, it matters to them because they're almost always working in kilojoules, so they want this value for F. And it's strange we don't teach this because battery renewable energy is huge technology right now, and this would be a great field to learn. But we teach a lot of organic, which was historically done for the big oil boom in the 1960s. I mean, I can't complain about it too much because I'm an inorganic chemist who's teaching organic chemistry now. So I'm going to teach you things that are not the way an organic chemist would think about it. But in Wake Tech doesn't offer inorganic chemistry or analytical chemistry or material science, so I can't teach that. All right. Question about the electrons being transferred. Let's see what this is. So typically, I'm never going to pair a balancing a redox reaction with a Nernst equation problem. And the reason I'm not going to do that is it's too easy to make a mistake balancing the redox reaction. When you balance a redox reaction, you break it into two steps, the oxidation step and the reduction step, and you multiply them in such a way that the number of electrons lost by oxidation equals the number of electrons gained by reduction. So with balancing redox, there's no shortcut. You had to break it into half reactions, balance the half reactions, and then come back, combine them, and then balance out the oxygens and the hydrogens. When it comes to working with the Nernst equation, if you're given a balanced redox reaction, you can take a shortcut. And the shortcut is to pick the easiest element to figure out. Because with balancing redox, they're not balanced, whereas with a balanced redox reaction, they are. And so easiest thing to do with a Nernst problem where you're given a balanced redox reaction is just to find the element that it's easiest to figure out the number of electrons transferred. So particularly if you had something like, and we're just going to pretend this one's balanced. So you could work it out for manganese, and you could figure out the oxidation states in manganese, and you've got two on both sides, so you have to change the change in oxidation states and use that to figure out the number of electrons transferred. But again, we're just going to pretend this is balanced. We know copper is 0 here, and we know it's +2 here. So we can just look at the copper and figure out the number of electrons that are transferred with the copper and say, well, it's a balanced redox, it has to be the number of electrons that were transferred between the manganese atoms. Now again, we can get by with this shortcut with a balanced redox reaction because we know the electrons are already balanced between oxidized and reduced species. If you're balancing a redox reaction from scratch, you can't make that assumption. So you have to go through, figure out the number of electrons transferred both by the oxidation and reduction reaction, and use multipliers to balance them out. So yeah, to answer your question, there is a shortcut. Pick the element that's by itself and figure out its change in oxidation state for a balanced redox. But it's not the same simplifying assumption we can make for balancing a redox. Now, in terms of units for standard reduction potential and the cell potential, they're both volts. Voltage and volts are used synonymously a lot. They are not necessarily equivalent. At this level, it's fine. It's kind of nuanced details. But yeah, the units are volts. Okay, so we want to do a balanced redox problem from WebAssign. First thing I'm going to tell you is that WebAssign problems are much, much harder than anything you're going to see on the final. But let me bring it up. Current assignments. Now for these balancing redox reaction problems, some of these are half reactions, some of these are full reactions. A comment on just these problems in general. I had to put water and H plus on both sides. Otherwise, you can actually kind of reverse engineer what the answer should be. So if water appears on one side and not the other, you're just going to throw a 0 on the side where it doesn't appear. Half reactions are the easiest ones to do, so we'll start with those first. And it actually looks like, yeah, someone wants to do 3 and 6. So I'm going to flip the screen really quick. So this is question 3. We have triiodide. Goes to iodide. And we need, it's implied here that the electrons are on the right side. And the other problem you want to work at 6, and this is the full redox. Ooh, yeah, that's a nasty one. So we'll deal with those. So for the first one, there's a little bit of a trick with this one. Triiodide is made by taking iodine and I minus. So we actually have 2 oxidation states here. We have I2 and I minus by itself. Now, with any redox reaction, you want to balance the oxidized or reduced species first. So we've got 3 I negatives on the right and an I3 minus on the left. If we were to look at the number of electrons it would take to make this work, we've got a -1 here and 3 -1s here. So if we put the 2 electrons here, now we've accounted for the reaction. Now, that's it. That's how you balance this one. So you need a 3 in front of the I minus and a 2 in front of the electrons. So yeah, actually this one works pretty well if you just look at the charges. Sorry if it came across as really way too easy, but that's how you balance it. Question 6. So for question 6, we have iodate plus whatever this compound is, H2N2O2. Goes back and forth to HNO2 plus hypoiodide. So to balance this reaction, this is a full redox reaction that's going to require you to break it into the oxidation and reduction parts. So in order to do this, we need to assign oxidation states to each of the non-oxygen hydrogen elements. So with all of these problems, oxygen is -2 and hydrogen is +1. Is that always true? No, you can generate peroxides, you can have hydrogen gas, but for simplicity at this level, we're going to keep oxygen as -2 and hydrogen is +1. So if oxygen here is -2, this puts iodine at a +5. We have +1 on each of the hydrogens, a -2 on each of the oxygens. So this is going to put nitrogen in a +1. For HNO2, oxygen's +1, oxygen's -2, so this is going to put nitrogen in a +3. And iodine here is in a +1. So that's quickly how you go through the oxidation states. I have videos where we actually talk about how to do these, but let's focus on the bigger problem here of actually balancing this redox reaction. So what you need to do is find the oxidized and reduced species. So oxidation is losing, it's becoming more positive. Wait, 4. Oh, sorry, looked at the wrong one. So in terms of who's losing, we've got nitrogen losing and iodine gaining. So I'm going to write the two reactions out. We have H2 into O2 going back and forth to HNO2. And we have IO3 going back and forth to IO -1. Charges again, +1, +3, +5, and +1. First step, when you've broken them to the half reaction, is balance it like it's a half reaction. First step is always make sure you've got the number of oxidized or reduced species being the same. 2 nitrogens here, 1 here. So we need to put a 2 in front of the HNO2. Iodine is 1 to 1, so we're good in that regard. Now we have to figure out the number of electrons being transferred. If you're being oxidized, your electrons always go on the right side. If you're being reduced, the number of electrons go on the left side. Iodine is the easiest to do. It's going from a 5 to a 4. We've got one of them doing it, so that's 4 electrons. Nitrogen is going from a +1 to a +3, which is 2 electrons, but we've got 2 of them doing it. So it's not the number of electrons being gained or lost by each nitrogen, it's the total number of electrons. So in this case, we're going to have 4 electrons lost. Now, the point of this problem is that if you don't make that connection, if you just say, well, nitrogen's going from +1 to +3, so I add 2 electrons, you're going to double this and get the wrong answer. The number of electrons being lost by all the nitrogens together here is 4, and so since they're the same number, we can add these together, and what we'll get is this. So IO3 plus H2 into O2 goes back and forth to 2HNO2 plus IO -1. We are now balanced in terms of number of electrons, so now we're left to balance oxygen and hydrogen. Few comments. Some books, most books, and most instructors will tell you to balance oxygen and hydrogen in these steps. Do not do that. Take it from someone who's spent years in the field. You do not need to balance water and oxygen in these steps. You can balance them up here and be right. The reason why I discourage you from balancing it down here in the half reactions, if you don't add and subtract them correctly, you're going to end up getting incorrect answers for algebra mistakes. Balance oxygen and hydrogen last, and in that order. So in terms of oxygens, 3 here, 2 here gives me 5. I've got 4 and 1 that gives me 5, so my oxygens are balanced. In terms of hydrogens, I've got 2 here and I've got 2 here, so my hydrogens are balanced. So my net reaction here is just this. And if we go and look at the actual WebAssign assignment, that's what it ends up being. We have no hydrogen and no water on the left side, 1 iodate, 1 H2NO2s, goes to 2 HNO2, 1 hypoiodite, and 0 and 0 for the hydrogens and the waters. The 2 is in front of the HNO2 because we need to balance the number of nitrogens. So right here we've got 2 nitrogens on the left side and only 1 on the right. This 2 creates the same number of nitrogen atoms. So it's just how you would normally balance a reaction. We don't bother balancing hydrogen oxygen to the last steps. The reason we can get away with this is this AQ subscript that appears in the problems. Because it's in water, we can let the water participate in the reaction. So if we need water to balance out, we just draw it from the solvent. If we need hydrogen, we just draw it from the H plus that we know is present because water breaks apart H plus and OH minus. So the only elements we have to balance are non-oxygen and hydrogen elements. We balance those manually, and then if we need to balance oxygen and hydrogen, we do that later with water and H plus. I would not say balancing redox reactions is hard, it's just tedious. It's a lot of attention to little details that by breaking into these half reaction steps, it lets us focus our attention on one particular detail as we move along. So again, the homework is not representative of the final exam. The final exam is much simpler. Definitely, that said, there's only so many redox reactions I can give you, and the homework ended up kind of being like the hard-ish range of the problems. If you look at the problems that are in the packets, they're hard-ish, but again, if you can do the homeworks and you can do the packets, you can balance the redox questions on the test just fine. I wonder what your next discussion board is. Okay, that makes sense. As you'll also see, this is the hardest part of the redox, the electrochem component of the class. The next stuff you're going to talk about for the discussion board Wednesday is the plating equation. That's just plug and chug. So to answer, Isaac's asking about the, not familiar with oxidation states, and H plus is plus 1, oxygen is minus 2. Assuming those are concrete, is that why you focus on nitrogen to balance charges? Yeah. We're going to kind of do easier, they don't look easier, but they are easier redox problems because oxygen and hydrogen are being kept in those oxidation states, -2 and +1. Harder graduate courses will involve peroxides where oxygen's in -1. They'll give you hydrogen gas, and which will hit you in -1 oxidation states, and it's hard to tweeze out where those peroxides are. So this is, again, the attention to detail. We can focus ourselves on the, because we're making this stipulation that oxygen is -2 and hydrogen is +1, we can focus our attention more to the non-oxygen hydrogen elements for looking at the charges. Again, a graduate course, you don't get to make those assumptions, but you're not in graduate school. And really, at that point in your career, you're so comfortable, you should be comfortable enough with oxidation states that if I put oxygen in -1, it's not going to throw you off that much. Again, it's an assumption we're making. It's going to be true for this class, and I just want to put that caveat on there. It's true for this class. If you go on the internet, you're going to find problems where they don't keep this true. Yeah, so manganese is in +8. It finishes in a +2. Manganese is one of the few that can go that high. It does exist in those oxidation states. So going from +8 to +2 would give you a, I'll write it up so people can see it. So we have 8H plus MnO4, and this should be Sn, not Sn plus 2. Goes to 4H2O plus Mn plus 2 plus Sn plus 2. So here we have manganese in a +8 going to manganese in a +2. There's your 6 electrons. We also have 10 going from a 0 to a +2. There are 3 10 atoms doing it, so that's 6 electrons total. Good. You can go on to higher levels of chemistry now. You can feel really smart. Like, go take inorganic chemistry and have to learn a whole field of math. Balancing one more problem, sure. So let's pick one of the full redox reactions to balance, just because those are the harder ends of the spectrum. So the next redox reaction we'll balance, we'll do number 5. And yes, even in class, these are ones that are, this is where we would spend most of our time, is going over how to balance redox. Now again, the final exam is going to have a balancing redox problem on it. It's not going to be nearly as hard as these. It's much more to the point. It's just, this is what you happen to get with trying to like teach this. So we've got nitrite plus hypochlorite goes back and forth to nitrogen monoxide and chloride. So again, we're going to go first step. We got to figure out who's being oxidized or reduced. Doesn't matter if you're doing a full redox or a half redox or a half reaction. Nitrogen is going to be +3 because we're treating oxygen as a -2. We've got 2 of them, and we need a -1 charge of the molecule, so that puts nitrogen +3. Chlorite, +1 for chlorine, +2 for nitrogen here, and +3 for the chlorine in the chlorite. So now we have to figure out the oxidized versus the reduced species. So oxidation is losing, meaning we're getting more positive. So in this case, we've got chlorine going from +1 to +3. So this is our oxidation reaction. And I'll write this up there, +1, +3. By default, our reduction reaction is this, but again, verify it. Sometimes even I make mistakes on these types of problems. We have it going from +3 to +2. It's getting more negative, so it's being reduced. So we've got NO2 -1 goes back and forth to NO. So we got +3 and +2. If you are reduction reaction, the electrons go on the left side. If you're an oxidation reaction, the electrons go on the right side. Now, the number of electrons is the difference in the charge times the number of atoms. So we have chlorine going from +1 to +3, that's 2 electrons. We have 1 chlorine atom doing that, so 1 times 2 gives us 2 electrons. For the bottom reaction with the nitrogen, and I'll actually write it beneath the glare so it's a little bit easier to see. We have nitrogen going from a +3 to a +2. That's 1 electron, and I have 1 nitrogen atom doing it, so that is 1 electron total. Now, what I want is these two numbers to equal each other. And to do that, I'm going to find the least common multiplier of the number of electrons lost by oxidations and gained by reduction. So in this case, the least common multiplier of 2 and 1 is 2. So I'm going to multiply the whole bottom reaction by 2. So I have 2 electrons plus 2 NO2s goes back and forth to NO. The reason I'm doing this is that when I add these two steps together, I want the number of electrons to cancel out. So when I put it back together, I get 2 NO2 plus ClO minus plus 2 NO goes plus Cl2 minus. So at this point, my electrons are balanced between oxidized and reduced species. Now I just had to balance the hydrogens and the oxygens. And again, you'll see a lot of videos where they balance hydrogens and oxygens here. Don't do that. It's a lot more work. To balance my hydrogens and my oxygens, I'm going to start with water. To balance it, I'm going to balance oxygen. So the left side, since I don't need these anymore, if I count up my oxygens, I have 4 here, plus 1 here will give me 5. Got 2 here, plus 2 here, which will give me 4. So I need to add water to the right side. And this water is going to balance out my number of oxygens. Hydrogen, pretty easy. Water is the only thing with hydrogen in it. So I need to add 2 H pluses to the left side to balance out my hydrogens. Now, a pitfall I see students fall into, and it's unfortunate that it does happen. Don't assume all the hydrogen comes from the water. Like, happens with a lot of problems, but just don't. Make sure you're counting the hydrogens. So Elijah wants me to go back through the 2 electrons for the oxidation reaction. So I'll do that really quick. This one. And I'll do it for the reduction reaction one more time just so you can see how I got the 1 for that. Each chlorine starts with a +1 and goes to a +3. So that's 2 electrons. And I have 1 chlorine atom doing it. So 2 times the number of chlorine atoms, 1, gives me 2 electrons. For the nitrogen, goes from a +3 to a +2, so the difference between those numbers is 1. I have 1 nitrogen atom doing it, so that gives me 1 electron total. And again, when I add them together, I want the electrons on the right to equal the number of electrons on the left. So to do that, I'm just going to multiply them by numbers until I get the same number of electrons. So if I multiply this whole thing by 2, now my electrons will cancel out. So this up here is the balanced reaction. Now we're going to take a leap of faith, and hopefully it agrees with what WebAssign has. So if you look at WebAssign, we've got the 2H plus that was on the left, the 2 NO2, the 1 ClO minus. On the right side, we have 2 NOs, 1 ClO2 minus 1, and the 1 water. Yes, so for this reaction, the total number of electrons transferred is whatever the least common multiplier of these two was. So if I were to give you this and say, okay, what are the number of electrons transferred? It would be 2, because if we look at chlorine, we go from +1 to +3, that's 2 electrons, or for nitrogen, oops, too far. Nitrogen, we go from +3 to +2, but we have 2 of them. So each one's gaining 1 electron, but there's 2 of them doing it. And again, to build on your earlier question, Isaac, if you've already got the balanced redox, you want to know the number of electrons that are transferred, stick to the easiest one. We've got one chlorine atom, so if we know it's changed in oxidation state, we know the number of electrons transferred. You can do it with nitrogen. It's going to be the same number because this is a balanced redox reaction. But you can kind of see the complication. It's one electron, but there's two nitrogens doing it, so you'd have to do that multiplication. So you're more likely to kind of get the number wrong if you do it with something that doesn't have like one atom of that element changing its oxidation state. So what should you know up to this point? You should be comfortable again with balancing redox. Balancing redox is more of a Chem 1 skill, but it's inconsistently taught. So be comfortable balancing redox, be comfortable with determining the number of electrons transferred, and be comfortable working with the Nernst equation, that E equals E naught minus RT ln Q over NF. By Wednesday, there is a formula for the plating equation, and the plating equation describes how much mass is gained or lost depending on how much current has flown. So give me just a minute to bring up the lecture notes, and I'll show you specifically what I'm talking about. Loading the PowerPoint right now. So if you go to the notes online, there's Nernst equation, standard reduction potentials. Come on, get in there. Know the anatomy of a battery. Pretty straightforward, but do go through and make sure you know what the anode side is, the cathode side is, and pretty much how a battery works. They're not that terribly complicated. And then there's this slide here about conversion. So this formula at the very bottom, I times T times 1.037 times 10 to the -5. Go through and learn how to determine the number of grams of something that is gained or lost based on the amount of current that is passed and for how long. And that will pretty much be the wrap up for redox and electrochemistry for this course. So Wednesday, know that plating equation, know the anatomy of a battery. I don't have a discussion board for it, but it does show up on the final exam. More of a qualitative understanding of how a battery works. And then next week, we're going to start the nuclear chemistry, and I think that's really it. Next week should be the last week of material before you take the final exam. Any other questions for today? I understand, like, redox is one of those, like, balancing redox is super hard. Don't get hyperfixated on it. You know how to balance a full reaction and a half reaction, but I'm going to update the discussion board, but it's going to take me about 10 or 15 minutes to get to the point where I've updated it, but you're going to pretty much see from what we've done today how it works. So the balanced redox reaction for today, 8H plus MnO4 plus Sn, 3Sn, goes back and forth to Mn plus 2 plus 4H2O plus 3 Sn plus 2. So that's the fully balanced reaction. The mistakes that are on the balanced reaction right now, there shouldn't be a 3 in front of this manganese. It should be by itself. And the charges are flipped. So it's Sn here, not Sn plus 2. Review day for the final? Yes. Typically the way I set up Chem 2, when I teach the course, the last day is dedicated for final exam review material. We're going to find, it depends on the speed of the students, how well they pick up redox. It dictates if we have 2 days. I'm guessing most of you are not going to have any issues with picking up how to balance a nuclear reaction. They're very straightforward, and the half-life formula is just material. So if in the following days and the live streams you decide, hey, I really want to talk about this previous material, you're free to do so with priority given to the current material. So if you want to go back and talk about IMF, we can. That's fine. Yeah, I've got my notes right here to actually like tell me what I need to be doing. So but yeah, probably the next 10 or 15 minutes I'll have all that updated. And again, the discussion boards are not meant as like a punitive grade. I'm giving you 10 points to encourage you to do it. But a lot of you have probably seen already. If you go back, and I'll put a comment saying, hey, you didn't say this, you didn't say this. If you go back and you do it, I'll give you the points back. This is not meant to be like a high stakes assignment. The point is to get you to do it and to get you to engage. So there is a mild penalty associated with you doing it wrong. I'd like you to go back and do it right. But don't like freak out on these things. If there's mistakes, I'm going to go back and correct them. If you're having struggles, let me know. I'd rather you do it and figure it out. The high stakes ones are the exams. That's it. So, and as we get closer to the final exam, we'll talk more about what's going to be on that. But yeah, view the discussion boards as more of a way to articulate and talk about the material. So you can explain to yourself how it works. Again, I don't want you to take these discussion boards as like, oh, they're so hard. They're not meant to be super hard. You got the package and you got the homework for that. It's more for me to gauge how well you're understanding the material. And what is the delta G in the problem? So there is a connection between voltage and free energy potential. And this is actually something that kind of gets lost from us doing this online. When you derive the Nernst equation, what you get is that delta G over NF equals the voltage. So if we know the delta G, we know the number of electrons, we know Faraday's constant, we can figure out the voltage. Conversely, we can rearrange this. And if we take the voltage times the number of electrons times Faraday's constant, that will give us the delta G. So in a traditional seated course, sorry, it's sitting right on top of that glare. In a traditional seated course, we would actually prove this relationship, which makes it a little bit more informative. But for this, because we're not here to derive the Nernst equation, this is the connection between the two. Yeah, you're very welcome for the streams. Like, this is meant to help you. We understand you didn't pay for an online course, so this close as we're gonna get to sweet. Yeah, I actually love deriving the Nernst equation because I didn't realize that until I started teaching this course where the Nernst equation came from, which is weird because my PhD was in electrochem and never made that connection. But when you take the material we learned back in test 3 and go, oh, it's just basically a unit conversion to get to Nernst, it's like, oh, yeah, that makes a ton of sense. Like, the Nernst equation isn't anything mystical. It's just the Gibbs relationship with units changed. Electrochem doesn't get weird until you start throwing calculus on top of it, which again, higher level course. Have fun there. But even in a lot of that stuff's actually not terribly bad if you have someone who can really explain it. All right, very welcome. So I'm gonna sign off now. I'm gonna be available via Teams and email if you've got questions today during the regular lab period. Again, the next live stream is gonna show up Wednesday. Thank you very much for showing up, and see you on Wednesday.